Hello, welcome to the massive series of linear integrated circuit, and today we will discuss about operational amplifier parameters. Basically, these all are the practical parameters of operational amplifier. So, first one is input offset voltage. So, in an ideal op amp, the output should be zero when both the inputs are grounded. Means अगर दोनों input हमारे zero हैं, then output must be zero. So, we can write here in an op amp, the output should be zero, when both the inputs are grounded. This is very important that if both of the inputs are grounded, then output has to be zero. But due to some imbalance in the circuitry, in all practical operational amplifier, there has to be some differential input to give our zero output. लेकिन ऐसा होता नहीं है. We will get some kind of output even when inputs are zero. So what we need to do, we have to provide some differential input voltage so that we can make this output to zero. This small differential input is called as the input offset voltage. So we can write here but due to imbalances in the circuitry, in all practical op amps, there has to be some differential input, to provide or to give a zero output. We need to apply this differential input so that we can get the output as zero. So this is we can write here the small differential input, the small differential input is differential input is called as input offset voltage. So simply we can say कि जब हमारे inputs zero होते हैं तो output zero होना चाहिए, but because of we have applied some power supply between in the terminal 4 and 7, so because of that we are not getting zero output, so we need to apply some differential input so that we can get zero output, and this differential input is known as the input offset voltage. So we can write here as IO, differential input voltage, as VC1 minus, basically this is the DC supply, VDC1 minus VDC supply 2. So this is the formulation of input offset voltage. VIO is equal to VDC1 minus VDC2. This is the some differential input voltage. So this is known as input offset voltage. Next is input offset current. So in ideal op amp, the bias current in both of the terminals should be same. Like this is the operational amplifier. We have output here and this one is inverting, non-inverting. This is V1. This is V2, and we have bias current as IV1. Here we have IB2. So in ideal op amp, these two currents should be same because there is infinite input resistance. These two current has to be equal, but because of imbalance in the circuitry, these currents are not equal. So whatever the difference of these currents is known as the input offset current. So we can write here for an ideal op amp, IB1 should be equal to IB2, but practically imbalance in circuit, but practically imbalance in circuit. Basically, differential amplifiers are inside of an op amp. So practically internal imbalance. We can write here internal imbalance in the circuit. These two currents are not equal in the circuit. These two currents are not equal. So the difference of these two currents, that is the difference of these two currents, non-inverting terminal and inverting terminal, both of these terminal currents, that is IB1 minus IB2. This become IB. This become, we can say this become IO. This become the IO is equal to IB1 minus IB2. IB1 minus IB2. This is the current in non-inverting terminal, and this is the current in inverting terminal. So the difference of these two currents, is known as input offset current. So this current is input offset current. This current is input offset current. So IB1 is current. Basically, this is the input bias current. Input bias current in non-inverting terminal. Similarly, this is input bias current in inverting terminal. So next is bias current. What do you mean by bias current? Bias current is the basically average of these two currents that is flowing in inverting and non-inverting terminal. We can write as IB is basically IB1 plus IB2 divided by 2. This is the input. This is the bias current. We can write it as bias current. This is average current. This is the average of IB1 and IB2. What is IB1 and what is IB2? IB1 is the input bias current in non-inverting terminal and IB2 is the input bias current in inverting terminal. So this is the bias current. Bias current is the average of these two currents. So next we will discuss about the slew rate. Slew rate that we had discussed earlier also. This is basically the change in the maximum rate of change of output with respect to time. If we are changing our input स्पॉन्टेनियसली द आउटपुट हैज़ टू बी चेंज. इनपुट में थोड़ा भी चेंज करेंगे तो आउटपुट में वो चेंज तुरंत रिफ्लेक्ट होना चाहिए. सो दिस डिफाइंस द मैक्सिमम रेट ऑफ चेंज ऑफ आउटपुट वोल्टेज with respect to time. So we can write here, the slew rate, we can write like the slew rate, the slew rate is defined as, slew rate is defined as the maximum, as the maximum rate of change, maximum rate of change of output voltage, of output voltage, maximum rate of change of output voltage with respect to time, with respect to with respect to time. So we can write, we know the slew rate for ideal op amp, for ideal op amp, we know the value of slew rate is that this is the infinite. But in practical op amp, we can write slew rate as d by dt of V output. This is the rate of change of output, maximum rate of change of output, that decided कि कितना frequent response output पर change होता है अगर हम input को change करते हैं. This is very important parameter, and the unit of this slew rate is volt per microsecond. This is the unit of slew rate, the change in output in microseconds. This can also be written as the maximum output voltage, let's say Vp into omega. That can be written as Vp into 2 pi f. What is f? F is the input frequency. This can be written as input frequency. And what is Vp? Vp can be written as the peak value of output voltage. This is the peak value of output voltage. So this is all about slew rate, and next we will discuss about the CMRR. CMRR, that is known as common mode rejection ratio. In short, it is known as CMRR. And this is the very important parameter that always tells us the noise rejection capability of operational amplifier. Noise को reject करने की capacity बताता है. For ideal op amp, we know that CMRR should be infinite. We know that CMRR should be infinite. In practical operational amplifier, this CMRR is defined as it is defined as the ratio of the differential voltage gain AD, ratio of differential voltage gain. In short, it is written as AD to common mode voltage gain. Common mode voltage gain can be written as ACM, common mode gain. So CMRR is AD divided by ACM. So for getting for getting ACM, what we have to do, like this is the operational amplifier and we are getting output from this 6-number pin. We have two inputs, inverting and non-inverting. This is V1, this is V2. So for calculating common mode gain, we will connect these two terminals and provide a common voltage that can be written as VCM. That can be written as VCM. So how can we calculate AD? That we know this AD is basically V output divided by VID, V output divided by VID, while ACM can be calculated as V output when both of the terminals are common divided by VCM. So this way we can calculate the CMRR, and this is the formulation of CMRR. It tells us the noise rejection capability, of any operational amplifier. So in ideal condition, VOCM is 0, so the ACM will be 0. Basically, see, if both of these terminals are common, so the difference will become 0. So what will happen? This will become 0, and if this becomes 0, the CMRR will become infinite. In ideal op-amp, that's why this CMRR value is always infinite. So this is all about common mode rejection ratio. So these all are the practical parameter of operational amplifier. So thank you for watching this video, and in next lecture we will discuss about open loop configuration of operational amplifiers.